In this video, we're going to talk about the different types of intermolecular forces. First, what determines the strength of an intermolecular force? Well, that's determined by Coulombs Law, which tells us that the attractive force between two molecules is a function of the magnitude of the charges on the two molecules. So the more highly charged or the more polar the molecules are, generally the greater the intermolecular force between the two molecules. And also r squared, that's the distance between the two charges, or in this case molecules. So the closer the molecules are able to get to one another, the stronger the intermolecular force. So let's keep that in mind when we're discussing these intermolecular forces. So the types of intermolecular forces, generally it's considered two major types. There's van der Waals forces and ion dipole interactions, or ion dipole forces. And under van der Waals forces, we have dipole-dipole forces, hydrogen bonds, and London dispersion forces. So let's start off talking about some of the van der Waals forces. In particular, let's start with dipole-dipole forces. These are attractive forces that occur between two polar molecules. So the molecules must be polar. And of course, the partially positive region of one molecule is going to be attracted to the partially negative region of a different molecule. Generally, the more polar the molecules, as we mentioned, the greater the partially positive, the partially negative regions, the stronger those two molecules will be attracted to each other. So the factors that determine the strength of dipole-dipole force is generally the polarity. As we mentioned, the more polar the molecule or molecules, the stronger the intermolecular force between the two. The second type of intermolecular force is a hydrogen bond. A hydrogen bond is it's very similar to a dipole-dipole interaction, where you have the partially positive region of one molecule interacting or attracted to the partially negative region of a neighboring molecule. The only difference is that hydrogen bonds are much stronger. In general, they're much stronger than a dipole-dipole interaction. And hydrogen bonds occur in molecules that have an oxygen-hydrogen bond, a nitrogen directly bonded to a hydrogen, or a fluorine directly bonded to a hydrogen. So if a molecule has an oxygen directly bonded to a hydrogen, a nitrogen bonded to a hydrogen, or a hydrogen bonded to a fluorine, then that molecule is capable of forming hydrogen bonds with another molecule of a similar type. So what makes a hydrogen bond stronger than a dipole-dipole interaction? Well, let me just state that in this we're comparing two molecules that are about the same size. So if you have a molecule that is polar and a molecule that is polar but can form hydrogen bonds, and those two molecules are about the same size, the molecule that can form hydrogen bonds will have stronger intermolecular forces. So what makes hydrogen bonds stronger than dipole-dipole interactions? Well, first of all, we mentioned that the hydrogen is bonded to oxygen, nitrogen, or fluorine, and these are three of the most electronegative atoms. So they're not only are they very electronegative, which means they pull the bonding pair of electrons towards them, but they're also fairly small. And we said that the two factors that go into determining the strength of an intermolecular force are the magnitude of the charges. So having a very electronegative atom is going to give you a very partially negative region. And they're also fairly small. So since they're small atoms, they can get very close to a neighboring molecule. So that makes these fairly strong. Now also we have to take into account the hydrogen atom. The hydrogen, of course, is bonded to the oxygen, nitrogen, or fluorine, And this hydrogen atom, of course, has only one proton, only one electron. And that electron, of course, is in the bonding pair. And so that bonding electron of hydrogen is going to be pulled away from the hydrogen, not all the way, but it's going to be pulled away from the hydrogen towards the oxygen, nitrogen, or fluorine. So essentially, since hydrogen just has one electron, the hydrogen atom is basically reduced to an exposed proton. So then you have a very a large partially positive region, and there's no electrons surrounding the hydrogen, so a neighboring molecule can get very close to it. So since the hydrogen has the only one electron, a neighboring molecule can get very close to it. Again, the distance between the two molecules will be very small. So that makes a hydrogen bond much stronger than a typical dipole-dipole interaction when we're comparing molecules of the same size, because you have a very highly partially negative region, a very highly partially positive region. And these atoms, the oxygen and the hydrogen, they're fairly small atoms, and so the molecules can get very close to each other. So here you can see a diagram of a hydrogen bond where we have the oxygen is covalently bonded to our hydrogens, and over here is a neighboring molecule. So this oxygen is very partially negative, and the hydrogens are very have a high partial positive charge. There's also not a very large electron cloud around the hydrogen. So there's no electrons around this hydrogen to shield it or repel this oxygen. So the oxygen can get very close to that hydrogen and make that a particularly strong bond. Here you can see several water molecules. You can have multiple hydrogen bonds between this. So one molecule can form multiple hydrogen bonds in the case of water. Our third and final type of van der Waals force is called a London dispersion force. All molecules are capable of forming London dispersion forces. So all molecules, whether they're polar or nonpolar, will be able to form London dispersion forces. But these are the only type of intermolecular force that nonpolar molecules can form. So they're particularly important for nonpolar molecules. A London dispersion force, basically it's a temporary dipole moment. Nonpolar molecules, their electrons are evenly distributed around them, but occasionally the electrons may be you may have more electrons on one side of the molecule than another. So this would be create a short-lived temporary dipole moment. When a molecule that's experiencing a temporary dipole moment gets close to another nonpolar molecule, it can induce a dipole moment in the neighboring molecules, and then these two molecules can be attracted with what's called a London dispersion force. So here's a little figure. Here we have two neon atoms, and the electrons on average are distributed evenly around the molecule, so it's nonpolar. But occasionally, some of the electrons, you may have electrons more on one side than another. So that creates a weakly partially negative region and a weakly partially positive region. So when this neon atom gets close to another neon atom, it disrupts or pulls some of the electrons towards the partially positive region, and this creates or induces a dipole moment in the neighboring molecule. So then these molecules are able to attract to one another. Generally, London dispersion forces are fairly weak compared to hydrogen bonds and dipole-dipole interactions. Here you can see a little different view of this. Here we can see the electron cloud of this atom and this atom. They're evenly distributed. And here the atoms have a induced dipole or temporary dipole moment here, and that induces a dipole moment in the neighboring molecule. So the factors that determine the strength of a London dispersion force are the size of the molecule. The more electrons a molecule has, the greater the magnitude of its temporary dipole moment. Also, the shape of the molecule. Molecules that are more linear tend to have more surface area to interact and form stronger London dispersion forces than spherical or globular molecules of the same size. Here you can see a chart with several hydrocarbons. Hydrocarbons are nonpolar molecules. Here we have methane, which is a very small molecule. And you can see as the size of the molecule increases, as we go down, the size of the molecule is increasing. You can see that the boiling point of the molecule is also increasing. So as the size is increasing, the boiling points are increasing. So these molecules can only form London dispersion forces, and the stronger the London dispersion force that they can form, the more energy it takes to disrupt that, resulting in a higher boiling point. So that's a measure of how strong the intermolecular forces are. So something like methane has a very, very low boiling point of around negative 161 degrees Celsius, whereas something like decane, which is a much larger molecule, boils at 174 degrees Celsius. So the London dispersion forces increase as the molecule gets bigger because they have more electrons, and so these temporary dipole moments have much larger magnitudes. Here you can see we talked about the shape of the molecule. Here you can see pentane versus 2,2-dimethyl-propane. These molecules are about the same size, and you can see that by looking at the number of carbons and hydrogens. They have the same number of carbons and hydrogens, but pentane has a higher boiling point than dimethylpropane. And this is because pentane is a more linear molecule, whereas 2,2-dimethylpropane is a more spherical molecule. So there's more surface area along pentane for two pentane molecules to interact than it is with a more compact molecule like 2,2-dimethylpropane. The final type of intermolecular force is an ion dipole force. Basically, this occurs when you put an ionic compound or dissolve it in a polar solvent, such as putting sodium chloride into water. The sodium chloride dissociates into its ions, into a positive sodium and a negative chloride ion, and then the polar solvent is able to interact with the positive cation and the negative anion by forming ion dipole interactions. Here you can see a picture of this. Here in the center we have our sodium cation, and it's surrounded by several water molecules. The water molecules are going to align themselves so that the partially negative oxygen is able to form an interaction with the sodium cation. So here we have they're all aligned so the partially negative oxygens are forming an interaction with the sodium. With the negative anion, the partially positive hydrogen atoms are going to align themselves so that they come in contact or come very close to the negative anion. So here we're forming each of these dashed lines represents an ion dipole interaction. So if we're talking about types of intermolecular forces, it's possible for some molecules to form more than one type of intermolecular force. So molecules that can form hydrogen bonds, they can typically also form dipole-dipole interactions and London dispersion forces. Molecules that are polar and can form dipole-dipole interactions, they can also form London dispersion forces. And nonpolar molecules, which form London dispersion forces, those are only capable of forming London dispersion forces. So it's possible to have molecules that can form multiple types of interactions. So take a look at this diagram, and it kind of gives you an idea of how to determine what type of intermolecular force a molecule can form. if we start here, interacting molecules or ions. Are ions involved? Let's say no. If ions are not involved, are polar molecules involved? If the molecules interacting are not polar, then only London dispersion forces can be formed. If the molecules that are interacting are polar, then we have to ask ourselves, are hydrogens bonded to nitrogens, oxygens, fluorines? If no, then the molecule cannot form hydrogen bonds. It can only form dipole-dipole interactions. If the molecule does have hydrogens directly bonded to nitrogen, oxygen, or fluorine, then the molecule can form hydrogen bonds. Now, as we mentioned, if it forms hydrogen bonds, it can probably also form dipole-dipole and London dispersion forces, but hydrogen bonds are generally the strongest type of interaction that it can form. Back up to here, if we say ions are involved, so if the molecules or if the atoms involved are ions, then we have to ask ourselves, are polar molecules and ions present? If so, then we can form ion-dipole interactions. If no molecules are present, just ions, then the ions are going to form ionic bonds.